this give rise to spin Hall effects? Well, in one simple mechanism called spin skew scattering, it looks kind of like this. So if you were here yesterday, this picture should also look familiar, except that there's a small difference. I don't know if anybody notices. Well, so here's our electron moving through a material, and there's a nucleus that scatters up. But now, unlike yesterday, the spin is now perpendicular to the scattering plane. It's not in the plane. But we know what happens. This electron moves. It sees this atom that scatters it, the nucleus that scatters it. So the electric field from the nucleus changes the momentum of the electron. But now we know also what happens, right? You have an electric field, you have an electron moving, so you see an electric magnetic field. But you actually see a magnetic field with a gradient, because if the electron is closer here, the electric field is bigger, the magnetic field is bigger. If the electron is further away, the electric field is smaller and the magnetic field is smaller. Now, if you have a gradient of a magnetic field plus a magnetic moment, we know what it means. It means there's a force. So if the spin is up, the electron gets deflected a little bit more to the right. If the spin is down, the electron gets deflected a little bit more to the left. Oh, sorry. Spin up to the left, spin down to the right. And it's a very simple homework problem if you want. So to convince yourself that if you go on the other side, spin up still goes to the left, spin down goes to the right. It's very easy to see. So here we have our source for spin-dependent scattering. And all that we took is we use isotropic scattering and spin-orbit interactions. These are two things that are in any material that you know. And therefore, these spin Hall effects happen in any conducting material that you can think of. Now, the question is, how big is it really? You know? So let me throw some more equations at you, just some phenomenological equations for spin Hall effects. If you don't get this slide, don't worry. But I thought for the mathematically inclined, they may like it. So, as many of you may know, when you look at the charge current, you can write a charge current and describe it by the so-called drift diffusion equation, where you have the charge current, here's the response to an electric field, the mobility essentially, and here's the response to a gradient in the charge carrier density. And so this is the drift and this is the diffusion term. Now if you also allow for spin polarization, you get actually two additional terms. You get these terms where it's a cross product of the field and the spin polarization, and you get one term that depends on the gradient of the, well, not really the gradient, but differences in the polarization. And so this is what's known as the anomalous Hall effect, meaning if you have an electric field and you have a ferromagnetic material so that the charge carriers are